We're going to prove their arc length formula for curves. But you need a smooth curve. If f is smooth on the closed interval AB, then L, which is equal to the length of the curve from A to B, A to B is simply this formula. L is equal to the integral of 1 plus the derivative of x, quantity squared, square root of the whole thing, dx. dx is not under the square root sign. And this is really easy to prove, actually. Proof. Let's look at a curve. So we have a curve. Maybe that's A, and this is B over here. And we want to find delta L. That is, we want to find the length of that little piece there. Well, you know what? That length is so small. And if you say, no, it isn't, you're right. I shouldn't make it smaller. And I should even make it smaller than that. And I should make it even smaller and smaller. And the delta x, that distance, it should go to 0. Okay. Well, I already said that this piece right here, that's delta x. And over here, so I made a right triangle. Well, I didn't make a right triangle because it's not a curve. In other words, I have this, that's the curve, and I'm doing this, and I'm going to approximate this length by this line. And if delta, so this is delta x. If delta x is small, it'll work. Okay, let's see what happens here. So if delta x is small, this will all work. So now, since it's going to work, let's continue. We'll assume delta x is small. So here is delta y. Let's look at this little region over here blown up a lot. This is delta x. This is delta y. Well, that length, Pythagoras would say, this is simple. That length, which we'll call delta L, is the square root of the change in x squared plus the change in y squared. That is delta L. This length right here is really close to that length if delta x is small. I mean, look at our picture up here. Delta x is small. And this little curve, it looks like a straight line to me. Okay, so we're going to play games with this. Delta L is the square root of x squared plus the plus delta x squared. The square root of delta x squared plus delta y squared. Now out of nowhere, I am going to divide by delta x squared. So out here, I'm going to multiply by delta x. Just remember, I'm really supposed to multiply inside. I'll just erase this in a moment. I'm really supposed to multiply, so I divide the bottom by square root of x squared. I'm really supposed to multiply the numerator by delta x squared. But if I bring the delta x squared outside of the radical, whether I bring it in front or in the back, it comes out of the radical as delta x. And there it is at the end. Usually we factor things out in the front. For example, if you had the square root of 100 times 2, you would bring the 100 in the front as 10 square roots of 2. But as opposed to saying the square root of 2 times 10. The reason is some people are a little bit sloppy and maybe they make this square root sign a little bit too long, and then it becomes confusing to them and others whether or not the 10 is underneath the square root sign. But for right now, we're really motivated to put it outside on the right. Alright, so now I have to divide each term in the numerator by delta x squared. I have to divide each and every term in the numerator by delta x squared. Okay. Now one of those fractions is simple, it's 1. The second fraction, well, that's the same as first doing the division and then squaring it. That's because both are being squared. Let's not forget about that delta x on the outside. Okay, now that is what delta L equals. Well, so now what we want to do is we certainly just don't want to find that length. We want to find this arc length and that one and that one and that one. Okay, we want to find all of these. In fact, we want to find the arc length straight through. Now, so we need to add up all of these small arc lengths. Now, the thing is that this is continuous. So when we add them up, we're not going to use the sigma notation for summation. We're going to use integral. When we add up all the L's, the delta L's, excuse me, we get the whole arc length. And when we integrate, basically, we're taking the limit as delta x goes to 0. Delta x is going to 0. So when it does, this fraction is just the derivative, which needs to be squared. And in the limit, that becomes dx. Now, if you don't believe that the derivative is, well, okay, look, the derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x over basically x plus delta x minus the x, which is delta x. Well, this is equal to the limit as delta x goes to 0. Clearly the bottom is delta x. Okay, normally we even write delta x in the bottom. Usually for the derivative, we even write it. Now, the numerator is the change in y. The limit of this as delta x goes to 0 is f prime of x. So that's why I get to call that f prime of x. And we're in x is going from a to b. And there is one way of showing that if you're going to integrate with respect to x, there it is. I'm not going to prove it or derive it, real similar, but you have a curve. Now, instead of x going from a to b, you go between these two functions. You go between, say, C and D. That is, y is changing. So somehow you want to finagle it. So in the end, the arc length is going to be adding up the y's. Instead of adding up as x changes, somehow you want to go from C to D, and you have to figure out what this is that you're going to integrate with respect to y. And but basically, it's just going to be dx over dy. Sorry, there's going to be 1 plus dx over dy, quantity squared, square root. Because we're just switching x's and y's. That's the only difference. Okay, so what goes in that box is what I just wrote up in circle now in purple. That's what goes in there, and you integrate from C to D. Try to prove it on your own.